Okay, so this is lesson 1 in our unit on quantum physics, and um, this one's the first 2 lessons in this unit are all about kind of some of the origins of quantum and some of the really important discoveries. This stuff you can find in your textbook, the Nelson Physics 12 textbook, on these pages, if you want that as a reference. And we're going to go through and we're going to fill in a lot of these notes, and we're kind of going to go through and chit-chat about some of the important findings and then how quantum resolved those things. So these are our essential learnings. By the end of the unit, we're going to have talked about the fact that Max Planck observed the spectrum of blackbody radiation, and he had a couple hypotheses, but basically he was the first person really that said that the energy from a black body comes in discrete parcels or packets called quanta. The energy of a photon is given by E is equal to h, which is Planck's constant, times the frequency of that photon. And we're going to look at the photoelectric effect, and that's an effect that was explained by Einstein, and the fact that electrons are ejected from a metal when light with a certain minimum frequency strikes that metal, and how this is an example of the conservation of energy. So let's talk first about blackbody radiation. So really, blackbody radiation is when really any opaque object, that's what we refer to as a black body, that has a temperature above absolute zero, it's going to give off radiation, and most of the time it's going to be thermal, but you can feel how warm something is without actually touching it, right? So fire, or say an element on your stove top, this effect is known as blackbody radiation, and the characteristics of this radiation really depend on the temperature and the properties of the object. So we know, like at low temperatures, the wavelength of the radiation is mainly infrared, so it's mainly thermal. So think about when you first turn on your stove, the stove top, especially if you have an electric stove top. If you have a gas stove, this doesn't work, or range. But when you first turn on your electric stove with those coils, you can feel them start to get warm, but very, very soon, very quickly, the object, as the temperature of that is increasing, the object begins to glow red. Okay, and if we were to continue to increase the temperature more significantly, at very high temperatures, the object would appear to be emitting white light. And so a good example of this, because this doesn't happen with a stovetop, hopefully, but a good example of this is in grade 9, when you burned that magnesium metal in the Bunsen burner flame, it got really bright really, really quickly, and so that the object appears to be emitting white light. Okay, so a couple of things about this phenomenon. Okay, when we do this. So the temperature of the object is increased, then the thermal radiation that it's emitting consists of a continuous distribution of wavelengths. And those wavelengths come from the infrared. When it starts to glow, it comes into the visible spectrum. And we can also have some light in the ultraviolet portion of the spectrum being emitted. Okay, and so if we were to look at, say, this graph here in your notes, and we were, the colored bands represent what actually happens with low temperature, and then medium temperature, and then higher temperature. A couple of things that's interesting to note. The first is that as the temperature increases, okay, the peak of the curve shifts to smaller wavelengths. Okay, and we can see that, right? So here's, you know, the peak of the red curve is kind of here. The peak of the green curve is now shifted to a lower wavelength. And then we even come over here and we can see, okay, well, the peak of the blue is shifted to an even lower. And yes, I know these lines aren't straight, but this is just an approximation, right? So we can see this shifting peak length as we get hotter and hotter and hotter. So that's one observation that we've noticed, okay? The other observation that's important to note is that the total energy which is related to the intensity of the light, increases with temperature. Okay, so as here's intensity on this axis here. As the temperature goes up and up and up, you can see that the intensity, or the energy that's being emitted, gets bigger and bigger and bigger. Okay, so it becomes more and more intense. So scientists kind of set out to explain this phenomenon. So this was something that people had observed for a long time, and scientists tried to explain this. So Wien's law explains the shift in peak wavelength according to different temperatures. So this rule right here, this kind of equation, is what predicts this peak wavelength at each of these spots. So if you ever wanted to know, say, what's the peak wavelength at this temperature, Wien's law is the one that can predict that for you. Okay. Now, Lord Rayleigh and James Jean developed a theoretical equation, adequately known as the Rayleigh-Jean law. Okay, and it correctly predicted the intensity of visible light. So it was pretty good. Their law, it was theoretical in nature. It was pretty good at predicting what happened for lower temperatures and for visible light. However, what they noticed was that as soon as they started getting really high temperatures, right, as the wavelength continued to decrease, so as the temperature went up and up and up, and the peak wavelength went to smaller and smaller values, save for UV light, the theory fell apart, because classical theory predicted this curve right here at, say, 5,000 Kelvin, but what they actually saw was this curve here at 5,000 Kelvin. And they couldn't explain that using classical theory. So that was unexplained, and that became known as the UV catastrophe. Okay, because they couldn't use classical theory to explain this phenomenon. Okay, so, and now we enter the origins of quantum physics. Because in 1900, so this is the, around the turn of the 19th century. So this seems like a long time ago. And yes, we call it modern physics, but it does seem like a long time ago. Max Planck derived a formula for blackbody radiation that was in complete agreement with observation. But he had to make two assumptions. And assumptions aren't necessarily bad things. He just had to make these in order for his theory to work. So here's his assumption. First of all, the molecules that are in the black body can only have discrete values of energy, right? And those energies are given by En. So E sub n is equal to, I'm going to do this. It's too messy. E sub n is equal to n times h times f. So these are discrete energy values where n is some positive integer called a quantum number. F is the natural frequency of the oscillation of the molecules, and h is Planck's constant, where Planck's constant is 6.626 times 10 to the negative 34 joule seconds. So the molecules basically are only allowed to have discrete values of energy, right? So we say that the energy is quantized, okay? And so this is a neat little diagram that might help to explain it. So here's energy, kind of like an increasing scale. And we're going to start at, say, the lowest level down here, and we would say this is zero. This is like our zero energy level, okay? Our next energy level up is with like a quantum number of 1. So this would be some value of energy that's h times f. Our next level of energy up is our quantum state that has 2. So this would be an energy of 2hf. Next level of energy is, of course, 3, and this would be at 3hf. So this is what he's saying. What Planck was saying was that the molecules can only have these discrete values or energy levels, okay? And the second assumption, so this was the first assumption up here, was that the molecules in the black body can only have these discrete values of energy. His second assumption was that the molecules then emit or absorb energy in discrete packages, which, of course, later came to be known as photons. The molecules either emit or absorb these photons by jumping from one level to another and then emitting some photon of that energy, okay? The difference in energy between two levels is always hf, and so that means that the energy of a photon is h times f. Okay. Now, interestingly enough, we also know the universal wave equation. Think back to grade 11. V is equal to F lambda. Because we're talking about light, we're going to use C. And so then if E is equal to H times F, E is also equal to H times, not F anymore, but C over lambda. And that gives us another nice equation. E is equal to hc over lambda. And we have two different versions, one with frequency, one with wavelength. Okay, so let's do a little example of this. A metal bar is heated in a shop so that the peak wavelength in its spectrum is 2.6 micrometers long. Determine the temperature, the energy in the photons at the peak wavelength, and which part of the electromagnetic spectrum this is found in. So first, let's find the temperature. Okay, we know that lambda max, the peak wavelength, is 2.6 times 10 to the negative 6 meters. It's 2.6 micrometers. And so we'll use Wien's law. and we get lambda max is equal to 2.898 times 10 to the negative 3, and we divide that by the temperature. So this equation now is just going to be a little switcheroo. T is equal to 2.898 times 10 to the negative 3. We're going to divide that by the wavelength, which is 2.6 times 10 to the negative 6, and we get 1115 Kelvin as the answer, which, if we put it into the right number of sig figs, is 1.1 times 10 to the 3 Kelvin. Okay, moving right along. That's A. We want to know B. What's the energy of these photons in joules? So we have this now handy formula. E is equal to h times the frequency, or hc over lambda, and this is the formula that we're going to use. So the energy of these photons is equal to h, which is 6.626 times 10 to the negative 34, times c, 3 times 10 to the 8th meters per second, divided by the peak wavelength, 2.6 times 10 to the negative 6, and we get an energy of 7.64 times 10 to the negative 20 joules. So that's how much these photons have at this point in time. C kind of asks, what part of the electromagnetic spectrum is this in? Well, we could say 2600 nanometers, or 2.6, or whatever it is. What did I say? 2.6 micrometers is 2600 nanometers. That's infrared. And it would be a good assumption that we would say, okay, so this is warm, but it's not glowing. So this metal bar is quite hot, right? 1100 Kelvin, but it's not hot enough to be glowing yet.